So if you remember, we have talked about just the brief of the various types of forces, and this is in continuation with that. I have shown here is, for simplicity, a cylinder, because this is something that we all can easily relate. So if you remember, in kinematics we were always doing questions of motion, but we were always assuming first thing, object falls under gravity. You already know they keep on accelerating due to gravity at the rate of 9.8 meter per second square. Why does this happen? Because ultimately when the velocity is reducing, this force is becoming weaker and weaker and weaker. Hello students, welcome back to another class on forces. In today's class, we are going to talk about springs, that is some more effects of forces. In the previous classes, we have been talking about that when force is applied, the state of motion of an object changes, isn't it? Whenever you apply force, the state of motion of an object changes. Now think about this. If I apply force from both sides, like a balanced force, even then can it cause any change? Of course, yes. Even if its motion is not changing, it can change the shape and size of the object. So have you not thought about, applying force and deforming something? This is what we are going to learn today, that when we apply force, there is a possibility that we can change the shape, size of any object. Alright, but again reminding that we will mainly talk about springs in this particular unit, and then we will talk about solids in general in the upcoming units. But today we are discussing the behavior of springs. So without wasting any time, let's get started. Put down the heading, some other effects of forces. Alright, so forces acting on solids, stretch spring, the limits of proportionality and the spring constant, as well as Hooke's law. This is what we are going to talk about. Alright, so forces acting on a solid, it can change the shape, it can change the size. As you can see in this, you can squash a bottle and stuff like that. So this is another effect of forces. Since we are discussing about forces, it should be necessary that we should discuss this effect as well. All right, so stretch springs. Now we talk about spring. Why? Because springs play a very crucial part in many machines. They majorly facilitate the effect of restoring the positions, isn't it? Maybe a shock absorber and like shock absorbing springs you can have, where you can think of absorbing the force, giving more time and reducing the effect of force, isn't it? So there are a lot of things where we can imagine springs play a crucial role. That is what we are going to discuss today. But before that, let's talk about a basic thing here, that what happens when the force is applied. Of course, you would say there is going to be a deformation, isn't it? That is what I have shown here. Like, let's say this is a spring. When no force or no load is being suspended through it, then the length that it acquires is called its natural length. What do we call this? We call this as its natural length. Now think about applying a force in this fashion. We are suspending a weight through it. Why so? So that we know exactly what force are we applying. If we apply a force like this, can we quantify that? How much force is that? No. That is why we are using this mechanism by suspending load. So for example, if this is 1 kilogram, the force will be 9.8 or approximately 10 Newton. If these are two masses of 1 kilogram each, then 2 kilogram, then the force is going to be 19.6 Newton. What do you see? More force applied causes more deformation, isn't it? More force. Now you think about suspending more masses, it will keep elongating. This is what Robert Hooke also observed, that you increase the force and the deformation also increases in the same proportion. Alright, so let's talk about that. Springs are designed to stretch a long way when a small force is applied, so it is easy to measure how their length changes. Now the two terms, load that I was just talking about, the force usually weight that stretches an object or a spring. Then extension, the increase in length. All right, keep it in mind, the increase in length. So for example, if the length of this hypothetically, let's say, is 8 centimeter, then that is the natural length. If we suspend a weight and this becomes 10 centimeter, then we will say that the extension or the change in length is of course 2 centimeter. Now think about suspending one more weight and let's say the length becomes 12 centimeter, then the extension will become 4 centimeter, isn't it? So more load you keep suspending, more extension you will get. All right. So write this down. Write this down. The two terms, load and extension. Load is basically the force that we apply, and extension is the increase in length of the spring. All right. So now if you have done that, you pause the video. Whenever I ask you to copy down the important stuff, you pause the video and then you do that. All right. So Hooke's law, Robert Hooke, what did he suggest? He suggested that the force and the deformation are directly proportional to each other. And when I say directly proportional, I mean if you double the force, as was done in the last case, that if you double the force from 1 kilogram to 2 kilogram, let's say, like the weight from 1 kilogram to 2 kilogram, the extension was also doubling. So it became 4 from 2. That is what Hooke suggested. All right. So force is directly proportional to the deformation, and then there is a constant of proportionality, and we call that as the spring constant or the stiffness constant. All right. It depends on the type of spring. It depends on the type of spring. We will see how. Not every spring will behave in the same fashion. No. Some springs will easily extend. Some springs you will feel that you need more force to extend them. That is what this takes into account, that how stiff the spring feels. So can we say that if the value of K is more, then the force needed for the extension is also more. Hence, this can also be regarded as the stiffness constant. And what should be the unit of it? Since this is Newton and this is meter in SI unit, the unit of K should be Newton per meter, which you may also write as Newton meter inverse, isn't it? So this is the thing that Robert Hooke suggested, that force is directly proportional to the deformation, but the catch is not always this law is exactly obeyed. Maybe initially you would see this trend in the spring where you are doubling the load, let's say the deformation doubled. You triple the load, the deformation triple. That is where Hooke's law is being followed. But after a point, you would see that the deformation and the force are not following the same kind of proportionality. That is when we would say that Hooke's law is now not being obeyed. For example, let's say I make the force from, this is let's say 10 Newton, this force was let's say 20 Newton, and if I let's say make the force 100 Newton, so 100 Newton has become 10 times of 10 Newton. You don't expect the extension to also become 10 times. It might be slightly more or less, but it might not follow the exact same proportion. And in that case, we will say that Hooke's law is not being obeyed. Agreed that you increase the force, extension increases, but it does not follow the same proportion. And then we say that proportionality is not being obeyed. All right. So let's revise again. What are we learning today? We are talking about not force changing the state of motion, but force deforming an object. All right. Force being applied and deforming the object. Okay. So that is about Hooke's law. Now next we talk about the stiffness of a spring in a little more detail. All right. So stiffness of a spring, the higher the spring constant of a spring, the harder it is to extend or compress the spring. All right. So let's say these are two different springs which you can see. This one feels kind of a little stiff and you don't expect the deformation to go that much as you would expect in this slinky spring. So this has a low spring constant, that means you need lesser force for causing the same extension, isn't it? Or you can say you have more extension when you apply the same force. So this load and this load both look the same, but you can imagine this does not extend much, but this extends easily. That means the spring constant of this is less and this is more. How? Because you can write K is equals to F by X as I have written here, and therefore you are obtaining more extension in the second spring. That means the stiffness constant is less, isn't it? That is what we are trying to suggest here. Alright, so now you have an idea how spring behaves, and let's see what further possibilities do we have here. Alright, so now let's do a very simple numerical to understand how this is going. So the table shows 3 columns to record the results of an experiment to stretch a spring. Draw a load versus extension graph to see how extension depends on the load. Alright, so this is when there is no extension. So this is basically the case when there is no load and therefore no extension, and we can say that the extension is therefore 0 centimeter, and this is representing the natural length of the spring. So whenever I say natural length, is basically the length it would acquire when there is no force being applied. Now we apply a force of 1 Newton and the length becomes 17.5. So can we say that the extension is 2.5 centimeter? Of course yes, because it's not 17.5, it is the increase in length, and that is going to be 2.5. Similarly for this, it's going to be 5 centimeter. Why 5? Because now the length has become 20 and initially it was 15, and therefore the extension is only 5. Similarly, this is 7.5. Are you realizing something? That Hooke's law is being obeyed. You double the extension, you double the force, the extension doubles. You triple the force, the extension triples. Similarly, you make the force 4 times, the extension becomes 10, that is again 4 times. But now, listen to this carefully. Now when you apply a load of 5 Newton, the extension becomes 20. So 1 to 5 is like 5 times load, but extension is 2.5 to 20. So it is way more, that is like 8 times. So you make the force 5 times, but the extension becomes 8 times. That means the proportionality is not being obeyed. Alright, similarly here, now the extension is like 45 from 15, so it is like 30. If we wish to plot all these on a graph with load on the y-axis and extension on the x-axis, so let's mark the points. So let's say we are representing the extension in centimeter here, and we have to go up to 30. So let's make each block as 2.5 centimeter. Okay, so let's write the scale first. Okay, so let's write the scale. X-axis, the scale is, let's say 1 centimeter is representing 2.5 centimeter, alright, and y-axis we can write 1 centimeter, that is 1 column is representing, let's say if we have a scope of going up to 12, you can decide is 0.5 Newton. Now think about it, I will wait here, you try to plot the graph yourself and see if a straight line is being drawn. Alright, so now let's do this very quickly. So first let's plot the y-axis. So this is going to be 1 Newton, this is going to be 2 Newton, this is going to be 3 Newton, 4 Newton, 5 Newton, and therefore 6 Newton, right? We have to go up to 6. X-axis, first we have to go for 2.5, alright, so this one, okay, so 1, then 2.5, then 2, then 5, alright, then 3, then this is 7.5, then 4, this is 10, easy, right? No problems here. But now when you go to 5, it becomes 20. So 1, 2, 3, 4, 5, 6, 7, 8. So you go straight away here, isn't it? And then it is like 30. So that is like 12. So this is 8, 9, 10, 11, 12. All right. So somewhat here. So what do you see? You will be able to draw a straight line. Let's try to pick up a straight line from here, and you will be able to draw a straight line till this point. Okay, no problems here. But now you will have to draw a freehand drawing and try to join these, isn't it? So here it is obeying the Hooke's law. Now again, increasing the force is increasing the extension, but not in the same proportion. So we call this as, let's say, the limit of proportionality. Just for your knowledge, I'm going to help you further. Limit of proportionality. And then you can also comment on one more thing, that the slope of this, that is tan theta, is going to be F over X, that is force over extension. So that is basically your spring constant. So imagine if you draw a graph which is more steeper, then that would mean that the spring constant is even more, right? That is, it is representing a stiffer spring. All right. So some more about spring, that you apply a force, and what does spring try to do here? Spring tries to regain its original shape, right? This is what elasticity is. When you apply a force, the spring tries to regain its shape. Copy this down, then we move forward. All right. So now after you understand the behavior of springs, how they are able to achieve this elasticity, you apply the force, they try to regain the original shape, and that is how they develop that restoring force, right? So now we should talk about one more thing which is very practical, that sometimes you might need to combine springs to achieve some particular task. So you get many questions in situations you will be given that you have multiple springs and you have to predict something. So you need to understand how springs behaves. We are discussing two main combination. One is series and the other is parallel. So when I say series or serial combination, it is just like one spring and the load not straight away attached to the spring, but another spring and then the load, right? So what you can clearly see is that the same load is building up the tension in the two springs. So can we say that the first thing that we observe here, that the force that is translated in both the springs is the same, while extension, depending on, let's say, we can call it x1 and x2. Let's make it general, and we don't know what kind of springs these are. It might be made up of copper, this might be made up of steel. They might have same length, but they still can have different stiffness constant because of the different material, right? So what do we have here? Force same, but extension is being divided, right? So now what we are trying to do is, let's say the spring constant of this is K1 and the spring constant of this is K2. So what we are trying to do here is think of an equivalent spring. Okay, this is something that is going to be very useful for you in situations like this. Just to omit this and simplify this by a single spring, this is what we are doing. So let's call the stiffness constant as equivalent K. All right. So the same load, okay. So let's say the force applied is F, let's say the force applied is F, and this extends by X. So this should play the same role as these two combined. So let's say if this extends by X1, this extends by X2, then how much will this load descend? So you would say X1 plus X2. Let's say this extends by 1 centimeter, this extends by 2 centimeter, then the whole extension in the combined spring is going to be 3, isn't it? So can we write X is equals to X1 plus X2? Of course, yes. Then what is X? So we can write this as F over K equivalent, and this would be F over K1, and this would be F over K2. So 1 over K equivalent is 1 over K1 plus 1 over K2. Keep this in mind. In fact, you can generalize the formula also. if there would have been another spring in series, let's say R, P, Q and R, then 1 over K equivalent would have been 1 over K1 plus 1 over K2 plus 1 over K3. Okay. So that is the equivalent K, what support it will give you. So whenever you have such a question, you can replace these two by one spring. So I can take an example, let's say K1, let's say is 100 Newton per meter. You understand, when I write 100 Newton per meter, it is like you need 100 Newton to cause an extension of 1 meter. And let's say there is another spring whose stiffness constant is, let's say 400 Newton per meter. So this is quite stiffer. Then the equivalent value of K is going to be 1 over 100 plus 1 over 400. So K equivalent in that case is going to be 400 over 5, and that is going to be, so this is like 400, so 4 plus 1, so 400 over 5, and that is going to be 80 Newton per meter, isn't it? This is going to be 80 Newton per meter. That is the equivalent spring constant. Okay. So what does it feel like? Lesser K, lesser equivalent K means it is easily extensible, right? So when you combine springs in series, you are allowing them to extend more easily because you are having more springs. More spring means more scope of extension. That is why the equivalent value of K is turning out to be lesser than the constituent springs. This was, let's say 100, this was, let's say 400, then this equivalent is only 80. Okay, so two things to be kept in mind: force is the same and extension is being divided. Copy this down, then we move forward. All right, now let's talk about the other possibility, that is the parallel combination. So in parallel combination, we are talking about a rigid rod and then the springs being combined. So we are not taking into account the scope that it might tilt. Okay, so we are assuming that these two are very close to each other and there is no possibility of a tilt in that sense, and therefore we can write, let's say the spring constant of this is K1 and this is K2. Again, we are wanting to find out the equivalent K. So what can we write here? So again, the opposite this time. This time the force is going to divide, isn't it? So let's say if this spring has a force F1, this spring has a force F2, then can we write equivalent F? This, right? This has to bear the same load as these two combined. So can we write equivalent F, or the net F is F1 plus F2, but the extension is going to be the same, isn't it? The extension is going to be the same. So what are we going to write then? So we will write this K equivalent into X. This is K1 into X plus K2 into X, giving us K equivalent is equals to K1 plus K2, isn't it? And again, we can generalize this. If there are 3 springs, then it is going to be K1 plus K2 plus K3. Now think about parallel combination here. So when you are combining springs in parallel, you are giving it a lesser chance to extend. I can prove it. How? Again, take the same example where K1 was, let's say 100 Newton per meter and K2 was, let's say 400 Newton per meter. Then what is the equivalent K that you're getting? So the answer is going to be K1 plus K2 simply, that is 500. That means it behaves as a stiffer spring because you are giving more support to that spring, and which is not allowing it to extend that easily. So when you combine the springs in series, they easily extend. But you combine them in parallel, it becomes more difficult to extend that. So now you understand. Again, I am, this particular class is mainly about spring. So you should understand the two things. A spring has a natural length. You apply a deforming force, it builds up a restoring force, and this restoring force is basically the result of elasticity. And when you say elasticity, it is basically the tendency to regain the original shape. You try to stretch the spring, it will try to compress. You try to compress the spring, it will try to stretch, right? So it will always try to regain its original length. Okay, copy this down. We'll take a couple of numericals. Okay, so next let's talk about this numerical. Spring 1 has the elastic constant K and spring 2 has the elastic constant 2K. The springs are connected in series and extended by a combined distance of L. Alright, so can you imagine, it is the same question where there is one spring, let's say this, and there is another spring, let's say this. Alright, so let's call this as K1, let's call this as K2. Let's say this extends by x1 and this extends by x2. So what are they telling us? They are telling us that the combined extension of the two springs combined is like L, right? This is what I have written. But if the stiffness constant of this is K, this one it is going to be 2K. So can we write that equivalent K is going to be using the formula that we have just learned for series combination. Let's write it like this: 1 over K equivalent is equals to 1 over K1 plus 1 over K2. So 1 over K equivalent is equals to 1 over K plus 1 over 2K, and therefore the K equivalent turns out to be 2K over 3, isn't it? Are they asking us that? Of course, yes. The effective spring constant, the equivalent spring constant. So the answer is 2K over 3, but that is in option C as well and option D as well. So A and B cannot be the correct choice. Now they are asking us the extension in spring 1. Agreed. This will extend by some amount, this will extend by some amount, and these combined will extend by L. So since the force is the same now, so can we write K1 x1 equals to K2 x2? Of course, yes. So K1 is like K x1, K2 is like 2K x2. So x1 value turns out to be, or let's say x2 value turns out to be x1 by 2, isn't it? So let's put the value: x1 plus x1 by 2 equals to L. We are getting 3x1 by 2 equals to L, or x1 equals to 2L by 3. So what does this tell you? That this green spring is extending by 2L by 3, while this white spring is extending by L by 3. Can you think why? Because this is stiffer, and if this is stiffer, this will extend less as compared to this. So these two are combining and extending by overall L, but not equally. This is extending less because of more stiffness constant, isn't it? So now you understand, this is a previous year question, how this is being used. And now let's do one more before ending today's class. So today I wanted to introduce another concept. I wanted to take this specifically in a separate video so that we can emphasize and only focus on this particular topic, because we will have spring being discussed again in the next unit, that is work and energy, where we will talk about potential energy in a spring as well. All right, so but that is all for this particular relation like with force, but we'll do one more question before ending today's class. All right, so let's talk about this now. Two girls want to weigh a watermelon, but they do not have a kitchen scale. So they use a spring and a 0.5 kg bag of sugar to measure. When suspended, the bag of sugar stretches the spring by 25 millimeter, while the watermelon stretches the spring by 37.5 millimeter. Assuming that the extension of the watermelon is within the limit of proportionality, calculate the spring constant of the spring. All right. So let's do the first part. We'll apply F is equals to Kx, that is what we know now. And since this is written, it is within the limit of proportionality, isn't it? So F is, since it is a 0.5 kg sugar bag, so we do know that it's going to be 0.5 times 9.8, because the weight is mg, right? And the stiffness constant is what we have to find out, and the sugar bag stretches it by 25 millimeter. So let's write it as 25 into 10 raised to the power minus 3. Why so? We are wanting to convert that to meter, right? The SI unit. So the answer that I'm getting is 0.5 times 9.8 times 1000 and divided by 25. So what I am getting is K is 196 Newton per meter. So for every meter you need a force of 196. Then calculate the weight of the watermelon. Okay, so but G has to be taken as 10. So if you take G as 10, then the answer will slightly differ. So it's written in the question, so let's not change that, and let's make this as 10, and then the answer is going to be 200, of course. Okay, so the next thing, now let's calculate the weight of the watermelon. So as we know, F is equals to Kx. So now we know that force is what we have to find out. So let's write it as mg. K we have just calculated, that is 200, and x, the extension in case of watermelon, is like 37.5 times 10 raised to the power minus 3. M is what we have to find out. G has to be taken as 10 again. So be careful, if the value of G is given as 10, then you have to follow that. Alright, so this is 200 into 37.5 times 10 raised to the power minus 3. So let's do this calculation very quickly. So this is going to be 200 times 37.5 divided by 10,000. So this is 200 times 37.5 divided by 10,000. Okay, so I am getting 0.75. This is going to be 0.75 kilograms. All right. So you could also have done that, you know, F1 over F2 is equals to X1 over X2. If you don't do the first part and you only have to do the second part, then you can straight away apply the concept that the force and extension are in the same ratio, and if it was like 0.5 G, this would have been easier. This is an alternate approach, and the extension is like 25 in the first case and 37.5 in the second case. If you use that, you also get the same answer here, that is 0.75 kg. If you have done the question like this, there is no problem, you can attempt it like that as well. So I leave it up to you which solution you want. Alright, so now you know about force in a spring, and again, two things: you deform a spring and the spring builds up a restoring force. That is what is the main learning of today's class. This property is called elasticity. Alright, so Hooke's law, the proportionality, everything, series and parallel combination, I hope you have grasped everything that I have talked about. Next, we will be discussing the previous year questions in the upcoming videos, and then you will be able to apply all this as well. But that's all for this particular video. See you in the next video. Keep learning. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.